So the first problem we're going to do on our practice exam review is problem 2.42. And we're given three forces that are acting on a body here, and we're asked to write them as Cartesian vectors. And the key thing that you need to know in order to do this problem is that Cartesian vectors, we've used a lot of different terms for that. We refer to this as the rectangular form of a vector. We've also talked about it as just decomposing a vector into its x and y components. And even to make it more confusing, sometimes we don't say x and y components. Sometimes we say the I hat and j hat components, which are the individual vector components along the x and y axis. So I'm going to zoom in here on a full screen. And I think it's easiest when you do this sort of problem to just take each vector away from the body and redraw it. And I'll begin with F1, just doing them in order, no particular reason. And if we notice this vector is kind of aligned over here in the original drawing, what we would call the fourth quadrant, we know that it has a magnitude of 850 newtons. And when I'm decomposing into rectangular form or writing them as Cartesian vectors, what I try to do is envision whether or not I can write this vector as the sum of two vectors. And remember that vectors add according to the triangle rule, one of which is aligned purely in the vertical direction and another of which is aligned purely in the horizontal direction. And notice if I draw a vector purely in the vertical direction, in this case, that vector would be pointing down. And if I draw another vector purely in the horizontal direction, and if I arrange my horizontal vector such that the actual tail of it is aligned with the tip of my vertical vector, note that the 850 Newton vector actually satisfies the triangle rule. Namely, this vector is the sum of these two vectors because it is what is often referred to as tip to tail addition. So we call the vector that's aligned purely in the horizontal direction the x component of this vector. And that's one way that your book traditionally denotes the x component is they'll show the vector, they'll put it in parentheses, and then put a subscript of x. And in a similar fashion, I'm trying to stay color-coded to that, they call the vector that's aligned in the vertical direction the y component. So the question is, do we have enough information? We know that this is a right angle, right, by definition, because the horizontal component and vertical component, or x and y axis, are perpendicular to one another. But the question is, do we have enough geometrical information in order to do this decomposition? Now, unlike the other two forces in this example, we're actually given information not about an angle, but about how there is kind of a similar triangle that describes how this vector decomposes into components. So we know now, we didn't know this when we were in chapter 2, that the reason that we can use this kind of similar triangle approach is that a force that is exerted by a cable has to be aligned in the direction of the cable. And what this is kind of showing us is that the direction of the cable, and in this case, the direction of the force, is defined by this force triangle. So if you think about this, typically, at least I feel more comfortable if I'm decomposing in terms of some angle. So I'm going to denote this angle that represents the intersection of the horizontal component and the hypotenuse as theta. And whenever the book gives you similar triangle information, what that means is that this force triangle has similar geometry to this geometrical triangle. So we can use this in order to solve for any interior angle within our force triangle. So note that if I define this angle theta as the intersection between the horizontal base and the hypotenuse in this right triangle, that by definition, the sine of theta, and just to refresh, I'm sure that everyone knows this by now, but the trigonometric principle we're using here is SOHCAHTOA. We know that the sine of this angle is defined as the ratio of the opposite side length divided by the hypotenuse. Relative to this angle, the opposite side length is 3, and the hypotenuse is 5. So we don't know what this angle theta is, but we know its sine is 3/5. In a similar fashion, we can define the cosine of this angle as the adjacent side length divided by the hypotenuse. So 4 divided by 5. So when we actually go and do this decomposition, right, and I'll begin by actually writing an expression for the x component, what we note is that it is adjacent to this angle. So in a similar fashion, we could write that the and I'm going to kind of go up and show you my work beneath. The cosine of theta is equal to the adjacent side length, which in the force triangle is the x component of the force, divided by the hypotenuse, which is 850 newtons, which means that I can solve for the x component of the force as simply multiplying the hypotenuse value, which is the magnitude of the force, 850 newtons, times the cosine of theta. And in addition, we know from our equivalent triangle over here that the cosine of theta can be written as 4/5. So all that I need to do is make that calculation, and we'll make that in a second, and that will tell us what the x component of that vector is. And the reason that we don't need to make any adjustment to the sign is because that component points or is aligned in the positive x direction. So that is in contrast to the y component here, which points in the downward direction. So when we do this decomposition and treat this initially just as a side length, we're going to have to add in a little negative to account for the fact that that's going in the negative y direction. But that is going in the plus x direction. And it is late in the day and my brain is dead. So I'm going to pull up a calculator just to make sure that I don't do anything stupid here. So 850 times 4/5 is going to be 680 newtons for that answer. And we don't have to worry about rounding or significant figures because it came out to be a whole number. So in a similar fashion, hopefully, actually this will be the last one I show just so everyone sees how this works. If I look in my force triangle, what would the sine of this angle be? Well, it would be the ratio of the opposite side length to the hypotenuse. So it would be the y component, and I forgot to go back to my blue pen, but that's okay, divided by the hypotenuse, which is the magnitude of that force. So what that means is if I solve for the y component of the force, it's simply going to be the force magnitude times the sine of theta, which we know based upon our equivalent or similar triangle is just going to be 3/5. So if I do that math, 850 times 3/5, actually type in the whole thing there, I'm going to get 510 newtons. But don't forget, as I said at the beginning, we look at the y component of this vector and note that it is pointing in the negative y direction. So even though I originally, like this is true, just treating each of these forces as side lengths of a triangle, I'm going to need to make my negative adjustment. Don't forget to do that at the end. So this negative adjustment comes from the fact that the y component is in the negative y direction. It's pointed downwards. So we talked about a lot of different ways that you could express the vector given this decomposition. And I'll just kind of refresh that for you. If you know that the x component is 680 newtons, you can write it as 680 I hat. If you know that the y component is minus 510 newtons, you can write that as minus 510 j hat. And then you can show that this whole vector is in newtons. Or an alternative way that we talked about writing it was just to use this kind of triangular bracket notation, write the x component first, write the y component second, and then just put the units afterwards. So these two are equivalent. And if you wanted to go back and check, if you have extra time on your test, of course you could check the magnitude. You could say, what happens if I take the square root of the x component squared plus the y component squared? And of course, since I'm squaring it, it doesn't matter that that component is negative. It will turn out to give me the same thing, whether I square the negative or I don't. But if I take 680 squared and I square minus 510, take the square root, you will find that you get 850 newtons, which checks out because that is the original magnitude that we were decomposing. So where did that go? Oh no, hope it's still there. Sorry. I'm going to turn it back on. Sorry. That's the second time I can't, I had to re-record this video because of that. So be patient with me if you don't mind, and we will get it back up here. Good. So what we've shown here is that this turns out to be 150 newtons. So that checks out. So just if you have extra time on the test and you want to go back and do some checks, that's one way that you could check. So let's go back and do F2 now. So notice that F2 lives down here in what we would call the third quadrant. And if I try to write it as a sum of a component purely in the vertical direction and purely in the horizontal direction, that's how it would look. So this is going to be my x component. This is going to be my y component. And relative to the geometry that we're given this time, we weren't given dimensions of a similar triangle. I'm going to zoom out here just so you can see. Instead, we were actually given what will turn out to be the interior angle within this right triangle. So where is the 90-degree axis? Well, clearly it's always just going to be the 90-degree angle, I should say, It will always be at the intersection of the vertical and the horizontal component. I'm going to zoom in a little bit since I wrote small there. Now you see why I usually write these up before I actually do the solution. So that says 30 degrees in case you can't see. So we're now hopefully, and hopefully before you actually started watching this, you were in the habit that you could kind of look and say, okay, relative to that 30-degree angle, I know that this hypotenuse has a magnitude of 625. And I know that this x component is opposite to the 30-degree angle, and this y component is adjacent. So when I go and write the x component, rather than having to show that manipulation of the ratios every time, you can just do it like this. You can say, first and foremost, the x component points in the negative direction. So I'm going to make my sign adjustment right from the beginning. I'm going to write the magnitude, 625. And since this is opposite, I'm going to multiply by the sine of that interior angle, which I was given, which was 30 degrees. And for the y component, again, I'll do it the same way. Notice that it's pointing in the downward direction. So I'm going to make a negative sign adjustment. I'll take the magnitude, 625. And since it is adjacent to the 30-degree side length, I will multiply by the cosine of that angle. So let's actually do that very quickly, going into MATLAB, and hopefully the .cam won't crash this time, but it's going to be minus 625 times cos or sine for the x component of 30. And these are probably ones that some of you may have memorized, but again, as I mentioned, kind of a long day. Sorry about that. So I get an x component of minus 312.5. And for the y component, and again, what they're trying to show you here is it's not always the fact that the y component is related to the sine and the x component is related to the cosine. It depends on what actual geometrical information you're given. So I am going to write that down here. So full precision that's reported to me on my calculator. And then since these are the actual answers that I'm reporting, the vector written in Cartesian form, I'm going to go ahead and write it. And this time I'm just going to use my simpler form. X component, we got minus 313 to 3 sig figs. And y component, we got minus 541 to 3 sig figs. So you could check the magnitude. That's one thing you could do. Another thing that I should have mentioned is you could just look at this and you could ask yourself, hey, if I go back to the original drawing, what quadrant should this point in? Well, if it has a negative x component and a negative y component, it should be down here in the third quadrant. And if we look, that is exactly where F2 is, right? It has, we are proposing, based upon our answer, that F2 has a negative x component and a negative y component. So if I were to sketch a vector with a negative x and a negative y component, it would end up exactly where F2 is drawn. We could have done the same thing for F1. It has a positive x component and a negative y component, so it is over here in the fourth quadrant as we thought. So just real quick, I'll just write the answer here for F3, and we'll actually show the decomposition as well. But notice that it has a magnitude of 750 newtons. It can be decomposed into a forced triangle that's going to have a positive y component. This should say F3y, and a negative x component. This would be F3x. This is a 45-degree angle. That's some information that we were given on the original problem. So that says, in case you can't see, 45 degrees. So you notice that the x component is opposite and the y component is adjacent here. So I would just say that the, sorry about that, hitting the button, I don't want to zoom. The x component, notice that it's going in the negative direction, so I'm going to put the sign adjustment. It's going to be the magnitude, which is 750 newtons, and then since it's opposite, I'll multiply by the sine of 45 degrees. Now, of course, in this case, if you use the wrong trig function, you're going to get the same thing because the sine and cosine have the same value. The y component is adjacent. It's going in the positive direction, so I won't need a sign adjustment. It'll just be 750 times cos 45. And if we put that in there just to complete this all, let's just find out what 750 times cos 45 is. We know sine is the same thing. And that is, if you remember, it's root 2 over 2, which is like 0.707. So this turns out to be, and I'll write the answer and go back to the .cam in a minute, that F3 is going to have an x component of minus 530, rounded to 3 sig figs, and a y component of plus 530. And that's going to be in units of newtons. So going back to the .cam and just wrapping all this up, you see that's our final answer. That's going to be F3 decomposed into Cartesian form. Negative x, negative y should be up in the second quadrant, and it is. We could check the magnitude if we wanted. For F2, where do we have that answer? We have that here. We already checked that it's in the correct quadrant. And then for F1, we have that answer up here. So when you try to show your work, just since you're going to scan it and upload it for your exam, try to show that level of detail. I know you're on a limited time crunch, so it might be a bit challenging, but then if you have any little sign mistakes or things like that or rounding mistakes, I can look at your work and say, hey, they really knew what they were doing.